Okay, let us start. So is everything in order? You can see my screen?
Yes, sir.
Yes, sir.
Okay. So today what I will do, I will write a few small functions for doing certain things on linked lists. So I will essentially add to the file that I started writing yesterday. So that was sorted list. Okay. Uh, First of all, you recall that we have defined a node in our linked list as one containing an integer data item and a self-referencing pointer called next. And we have typed that kind of structure as node. Okay, so I will first illustrate, let's say, in addition to printing, this traverse function will also return how many elements are there in the list. Let us do it. So let n be the number of elements in the list. So I initialize it to 0. Whenever I see a new element, I increment that n. And maybe outside I will print. So let me stop this new line printing here. Just I will return n. Okay. So this is a small change I am making. I am printing all the things. And outside I will print the number of elements returned, and then I will put the new line. So let us go to our main function.
Uh,
Maybe
sir, sir, while
use
p and y equal to null is same.
what?
Sir, while p and if you write while p not equal to null, both are same.
Yeah. Null evaluates to 0. Anything non-null evaluates to true. So null is false. Anything non-null is true. So what I will do here, I will set size equal to this, and then maybe I will just print the size, and shall we do the same thing for this? This reverse printing will also return a size. So I will here again print size equal to %d, then \n, and here I will print size. So I have to change the code of this reverse print as well. Okay, so this is int. If age is null, then the size is 0. Otherwise, I will just store in S whatever is returned by this reverse print, the recursive call, and then I will print this, and then I will return. Can you tell me what I am going to return?
Sir, S plus 1.
S plus 1. Exactly. Okay, so let me just, okay, instead of making two big lists, I will just leave it between 10 and 20. Okay, so GCC warn all sorted list.c. Okay, so there seems to be some problem. From where is this L equal to coming? Oh, I see. I understand. Here also let me do this thing. Size equal to this. And I will just copy. Then let us see what happens. So L is empty, size is 0. Then it's a one element thing, two element thing, 3, 4, 5, 6, 7, 8, 9, 10. So there are currently no repetitions. Here also I do not see any repeated insertion. So let me try a few times. What happened? I'm choosing numbers between 0 and 99. So by the birthday paradox, there should be a repetition. It's high probability, but why is it not happening?
Sir, there are repetitions in the last line on the previous program, 55, 95, 95.
There was where?
I saw it 2 times, 55 and 95, 95, somewhere in the last line. Yes, sir.
Oh, okay. No, this is fine. No, there are repetitions. That is fine. But the number of nodes is 20 anyway. Because we are allowing repeated insertions. Okay, it's okay. Sorry, it's my mistake. So if 5 appears in the list, then I will not add it. That modification you can do. But for the moment, let us take this. Okay. No, this is fine. Sorry. Repetitions are okay. 49, but number of nodes is 17. Okay. Now I will demonstrate a few things. First of all, as I mentioned yesterday, I will do I was using age, right? Okay, so let me tell you what I mean by deleting a node with a value x. First, the first topic is deletion. So for example, let's say we have a list like this, something like a 5-element list. In this example, it is sorted, but it need not be in all examples. So maybe 5, 16, 37, 51, maybe just 58. Okay. So now I want to delete one node. Now there are several cases. Suppose I want to delete, let's say, something which is not in the list, maybe like 27. So I can search the entire list, do not find 27, or I can stop as soon as I found an element larger than 27, because this is a sorted list. But in general, if the list is not sorted, then I will linearly search over the entire list, do not find 27, so I return the original list. Then what may happen is I may try to delete the first element. If that is the case, So maybe I will use another color. If I want to delete the first element like this, then it is this element. What I will do, I will change the header from here to here. And if I am able to delete, it's a good practice, I free this node. Okay. Otherwise, if it is not the first element of the list, so let me use another color, something like 37 or 58. Okay. So let's say I want to delete 37, which is present. Okay. So this case, it is the first element. This I have handled separately. Otherwise, I would want to delete it. Of course, I should preferably free this node. And then what I will do, I have to sit on the node before this node. And then what I will do, I will change this next pointer from this to this. So that effectively this is cut from the list. But then there is no link to this. So I will use another pointer and free this node. Okay, that's cutscene. Even if you do not free this node, it will stay in your memory, in your malloc allocation area, and you cannot use that memory. So this will be called a garbage. So unless you free this node, this garbage will remain. Okay. So I will use some pointer that will point to the node before the node that I want to delete, and then this next pointer will be assigned next. This is fine, right? And this case,
Yes,
and I want to delete 58. This is basically the same. I will stay at the last, but I mean the previous node, and I will make this next. That will be empty. Okay, so that is fine. So let me now write this delete node. Only thing, delete function. Only thing I have to take care of the first node deletion. How many do I need? Maybe another node I need, just for another node pointer I need. Okay, so if this is a very special case, if it is already null, you return null. Nothing needs to be done, because there is no element in the list, and whatever I want to delete, it will have no effect. Okay, otherwise, I will handle first this special case, this one. The node that I want to delete is the first node. So if h data, okay, maybe I write x first. The data is found in the first node itself. What I will do, I will just for the moment store q equal to h. Or I will say q equal to, or maybe p equal to, okay, okay, whatever, yeah, fine, q equal to h, h will be h next, free q, so this is the courtesy, and then you return the new header. Happy or not? This is the first special case, the list is empty, then there is nothing to delete, simply return an empty list. Otherwise, if there is a match with the first node data itself, then I will temporarily remember that earlier header for freeing, then change the header from header to header next. Okay, and then I will say free queue. Then return this updated header. Okay, I mean returning is necessary because the pointers are copied by value. So even if I say h equal to h next here, whoever is calling, it does not see it. So I have to return it. Happy or not? Up to this point.
Yes, sir.
Okay, great. Otherwise, what I
Sir,
will do?
sir, you are deleting first node here.
Yes, because x is found in the first node itself.
Sir, I didn't understand why you have to do q equal to h and then free q.
No, you look at this picture again. If I want to delete this is my h, but not the original h, it's a copy of this pointer h. Okay, I want to free this node. So I temporarily remembered the address of this node. Then I change that header from this to this. But anyway, everything is called by value. So even if this h changes, nothing happens to the pointer that we passed in main. So later I will return this, and then earlier I have stored this queue. Okay, then free that node, then return this h. Is it clear now?
Yes,
So
sir.
for doing free of that, you are doing this, no, by storing its address in queue.
Now, what is the question?
So for deallocating that header pointer, you are using queue, no?
Yeah. For freeing, I am using this queue. Yes. It's just for freeing it. And if I am not worried
So
about,
if we do not have to free, then we can directly do h is equal to h dot next, like
you
that,
can
no?
actually do something. If this is not what you want, okay, I can simply say, if you are not, I would say, so you can simply say return h next. That's all. Happy or not? If I do not want to free, so forget this part of the code. If I do not want to free, I can simply return h next. So that I mean the when the main function says L equal to delete L, some x, whatever is there, then the earlier node, this earlier start node, the reference to that is lost. So this now becomes a garbage. You can no longer access it. Is that fine now? Okay. So it's fine.
Yes, sir.
It's not necessary that you will have to
Yes,
free, but it's a good courtesy. That's why I am basically promoting garbage collection in your program itself. Okay. Now, what if I swap this? I say q equal to h, then free q, then I say h equal to h next. Is there any problem? I swap this line and this line. Can there be any problem?
Yes, sir. The data of the next pointer in the first node will be erased. So that will no longer
Now,
be.
once you free this h, and after, let's say you first free q, and then you call this, but in between, so this h may be allocated to some other thing. So whatever h next now is, that is no longer in your control. Okay. Most likely with 99.99% chance, if it is only this code that is running, this will not happen, but it may so happen if there are many other codes that are running and you do not know what is called a time sharing. So This is safer. Okay. So you first execute this, then what is called your program gets preempted. Another program gets into execution. It asks for memory and gets the memory. Okay, whatever is there here. Then if you say h equal to h next, when it once again is rescheduled by the operating system, that h now contains something different, and accessing its next may be a bad thing. Okay, so this is a safe way of doing it. Okay. Anyway, so now what I will do, I will search for x while so given this, I know that okay. Maybe it's a good idea because this is a sorted list. So if does it matter? It doesn't matter.
So
Okay.
take for unsorted.
Up to this point, this unsorted thing will work, right? You are simply
Yes.
checking for
Yes, sir.
emptiness and the existence of the key in the first node itself. Okay. So this condition will change if it is an unsorted list. So here I know that whatever this P is pointing to, that data is not equal to X. Okay. So while P next not equal to null, or I can simply say while P next and P next data is less than X, so I am sitting at this initially, and I am looking at the data of the next node, not this node. It's not P data, P next data, this one.
Sir, what we are doing here is for the sorted linked list, right?
Yes. If it is an unsorted list, you can simply say not equal.
Not equal to, yes, that is.
Right. Yeah, that's the only difference. Okay. Now again see, there are two reasons why this loop may break. Either this condition becomes false or this condition becomes false. If this condition becomes false, this means what? P next is equal to null. What does it imply?
That is the end of the list.
So it means that we have reached the last element of the list.
Yes. Yes. So in that case, what should I do? If P next is equal to null, then I have not found. So I will simply return the original header H. Happy or not?
Yes.
Okay. So that is if this condition fails. Now, suppose that this condition didn't fail, but this did fail. Is there anything to check?
Whether it is equal to or greater than.
Exactly. So it failed means P next data is greater than equal to X. So if it is equal to X, then I will actually make the deletion. Otherwise, I will simply return the original list. Okay. So first I will check whether P next data, it may be greater than X, then I am again, this is not found. So I will simply return the original list. Okay. Otherwise, what shall I do? My P is here. I am using P here, right? Yeah. So my P is here. 37 is found here. And I want to free this. So what I will do, I will store as before. This is P next. Later I will free it. Then what I will do, P next will be either P next or Q next. Okay, note that P next is not null. If it is null, I am here. So Q next makes sense. This is Q is not null, therefore Q next makes sense. So I say P equal to Q next or P next equal to, sorry, P next equal to Q next or P next equal to P next. That is also fine. Happy or not?
Yes, sir.
Now I will free Q. Okay. So P points here, Q points here. P next becomes Q next. So this is just bypassing this node, and then I will free this. And eventually I will return H. In fact, I can club these things together. If it is equal to this, otherwise do nothing. Yes or no? If it is greater than X, then I will simply skip this and return H. Otherwise, I will make that bypassing, free that node and return H. Happy or not?
Yes, sir.
Okay, so let us run it. Let us try to delete something like 10 random values. So I will have this. I will simply copy this part and instead of insert, I will simply say L equal to delete L X. And then I will do whatever this. So here I write something so that it becomes, this is inserts. Here let me write deletes. Actually these are not deletes, deletion attempts. Okay, so let us see how it works. Oops, 16 not there, 2 not there, so nothing is there, right? 16, 2, 69, 3, 95, 17, 55, 15, 60, 50. So nothing is there, so that's why I am unable to, yeah. Here I am successful. No. I see. I have to write delete here. Okay. So it happens fairly rarely. So let's see. 11, it is not there. 70, it is also not there. 4 is there. It happens to be the first element. So this is taken out. 7, 8, 10, 25. So that is thing that is happening here. Okay. Okay. Now this is apparently a better example. I see many deletions. 85, not there. So size remains the same. 16, it is also not there, so size remains the same. Then I want to delete 86. It is here. So 84, 93, 95. So 84, 93, 95. Then if I delete 84, 84 is also there, so it will be 74, 93, 95, 74, 93, 95. Good. And then let us see where 61. It is there, so it will be 52, 52, 67, 68. After deletion, this is 52, 57, 52, 67, 68. Okay, so it's working. 67, it is there. 52, 52, 68, 72. 52, 52, 68, 72. Okay. Okay. Also, we have seen an example where the first element is deleted. Is ever deleted? Yes. Here, for example, the first element is deleted. 33, 36, 36, 36. Now this 33 is deleted. 36, 36, 36. Okay. Anyway, all cases are covered, and this apparently working. Okay. Happy or not?
Yes.
Okay. Now let us do something bit more non-trivial. So insert, delete, printing, reverse printing, these are all that we have seen. Now what I will do, let's go to the next slide. Okay. So this is my list L. Maybe just 4. Maybe 7, 32, 41, 48. Okay. Suppose I have something like that. Now I have these nodes associated with this. What I will do, from this L, I will generate 2 lists, LO, LE. Okay. This O stands for odd, E stands for even. So what we will do, after this function returns, I want to have an effect like this. LO, this is 7, this is 41. L even will be 32, 48. Okay. So this is what I would like to do, but I will not create fresh nodes for LO and LE, because I will use these nodes itself. So this next will point to this 41, this next will point to this 48, and somehow I need these 2 initial headers, LO and LE. Okay. I can keep on creating new nodes and copy these values from L to LO and LE as appropriate, but I will not do this. Instead, I will simply adjust these pointers so that this splitting is done. Do you understand this point? What I am going to do?
Yes. We'll just change the links, right?
I will just readjust this link. So if it is something like, if this is 48, well, This is 49. Okay. Then this will be 749. This will be 3248. So this will go to not next, but next. Okay. And this next one may be arbitrarily far away. May even be not there. Okay. So how do I manage it? Okay. So let me write the code. And first of all, let me introduce these two lists. Star L odd, star L even. Okay. So what I will do, I will write a function named split L. I have other. Okay. So I will have to add other parameters, but for the moment, let me write this code for this split. Actually, it will return two pointers. So we have to do something, but for the moment, let's say node star age. Okay. Okay. Then I will have these two headers, header odd, header even. I will also use two pointers, q. Okay. Okay, so let me do one thing. So I want values in both LO and LE. These two new headers. Okay. But I cannot simply pass them because everything is called by value. If I want to see a change in LO and LE, I have to
Pass pointers to them.
pass pointers. Okay. Okay. So here I will have node pointer LO, node pointer LE. So happy?
Yes, sir.
Oh. So let me handle this specific cases first. Then both LO and LB should be null. Then I will say return. Happy or not? It's not LO equal to null, it's star LO equal to null. So, do you agree? I hope this is fine, right? Otherwise, age is not null, so it is pointing to something. So what I will do, if age data %2, and if you, it's not needed, but anyway. What is age data %2? What does it mean?
Sir,
So
if it is
even
odd.
sorry, odd.
Odd, right? It is odd. So I have this header HO will start at H. Okay. Otherwise, header even will start at H. Okay. And maybe I use, instead of P and Q, I use P odd and P even. So what will happen is HO and HE will be the header. But whenever I find a new, I would say, next element, that will be appended at the end, not at the beginning, right?
Yes, sir.
So this PO and PE, okay, maybe this is head, this will point to the last node. So tail.
The POR P are the iterators for the like odd and even lists.
This header is first fixed, the
Yes,
odd
sir.
header and the even header. Okay. Do I need to do this? Let us not do this. I will simply write a loop. First of all, the header of the even or odd header and the even header, they are not decided. Okay. So they may be null also in case HO may be null if there are no odd elements in the list at all. If there are no even elements in the list at all, then HE will be null. So what I will do, I will iterate on H. This last thing that I will do is this. Okay. Now I will check if H data %2 else. So that means I have detected a new odd element. That may be the first odd element or maybe the next odd element. So if HO is null, this is the first element. I will set HO, also the tail, equal to H. Else what should I do? Okay, fine. I have to append that thing. Okay, sorry, at the tail O next equal to H, tail O equal to tail O next. Maybe it's a good idea not to do this here, so I will have another node. Star G. G equal to H next. And H equal to G. Why I am doing this? Is this needed? Let's see.
Yes, sir. So that the age it does not get like changed every time when we are turning
I
the
am,
loop.
am I changing H next? Am I changing H next? H.
No, sir. No,
I
sir.
am,
We are not changing H.
I am not changing H next, right? So this is not needed actually. Fine. I am not changing H next. I am simply either initializing the odd or even pointer, odd header and tail, head and tail to the first odd element found. Otherwise, I will not change the odd element, HO, odd header. But Taylor was the last element, its next will be H. Why is this necessary? Taylor is why Taylor. Oh, okay. So Taylor next or tail next will be this, and the Taylor will come to new tail will come to this next thing. This is fine. I am not changing H for the moment. Otherwise, I have to do the. I hope this is correct. Without drawing a picture. Otherwise, I have to do it in the event thing. So event list starts equal to H. Okay, H next.
Sir, can you explain this algorithm like once diagrammatically? What is happening?
I will see. I hope this is work. This will work. Then what I will do if this is not empty, I will draw a picture and let you know. I will explain it. H, sorry, not H. Tail equal to null if this is at all opened. This is equal to null. Okay, and then I will say star L odd equal to H odd, star L even equal to H even. Okay, let us see what happens. I will explain with a bigger example. Split. Maybe I'll just copy from here. LO odd will be this, size is this, and LE will be this, whatever the size is returned, and maybe I also print L. Okay, let's see what happens. So I will just write something here. This is called odd even splitting. First, let us see whether this works at all. We will see. Ten, 12, 14, 10, 12, 14, 46, 46, 50, 52, 64, 80. 23, 25, 53, 69, 97. Okay. Okay.
Sir, why is L only printing the order even?
This is the reason I have printed it. You tell why. Why?
Sir, we are delinking the odd values from L.
Yeah.
Sorry, like the other values from L. So maybe that is the reason.
Yeah, that is the reason. Yeah, we have reoriented the pointers. LO is the order list, L is the even list. L will point to either this or this, depending upon whether the first element is odd or even. Okay. Okay, so this is working. So I will now explain with an example.
Sir, why L is printing only odd one?
I will now give you an example illustrating how this works. Okay. Okay. Let's start with a bigger example. Okay. Okay. So I will no longer draw it that way. So let's say 2, 4, 6, 7, 8, 9, 12, and let's say 20. So this is my list. Okay. So what I will do, HO, HE initially null. Okay. Then this H will run here, 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 here. This H. Let us go to this. H is H next. This is what I am doing. Okay. So H will point to, H will run through this entire list. Okay. So here I see that I have detected an even element. So at this point, H, this is even. This points to this. Tail of this also points to this. This line, right? Sorry, this line. H even, tail even, both point to H. Okay. Then what I do, so which part of the code? First of all, this else part and this if part, that is executed. Okay. Then what I will do, I will advance H, so it will come here. And I see once again this is even. Okay. So once again this else part will be executed. This time this is not null, so this will not be executed. Okay. Then what I will do, what am I doing? LE next equal to H. Okay, again here there is nothing is happening. It is already H. LE next becomes this. Okay. So this is now this. Okay, so actually tail E, this is already this, but anyway, then I will say tail E equal to tail E next. So tail E
Sir,
now becomes
tail E, tail E next equal to H is for the cases where it is not consecutive, right?
So we will come to those examples soon. Okay, then again this H comes here. Okay, once again this is even. So tail E next will be H, which is actually already there. So that doesn't matter. But tail E will now go to this. Tail E next. Okay. So up to this point, HE, the header, then 4, then 6, and that is the tail. Okay. Then I make H equal to H next. Okay. Now I see this is an odd element, so I will set both HO and tail O to this pointer. So forget this. So this is which part? This is this part. Now this is odd, and this is both are null. So I set HO and HE to this. Okay. Then I make H equal to H next. Okay. So H comes here. And I once again see this is even. Okay. So this list should grow. So tail E next. Okay. This was earlier pointing to this. So I will say tail E next. I will change this pointer from here to here. This is what I am doing. Tail E next is H. Happy or not?
Yes, sir.
Okay. And tail E becomes tail E next. So tail E will come from here to here. Okay. Then again H is incremented. I mean incremented means H equal to H next. This is odd. Okay. Now these lists are open. So tail O dot next will change to this. So I will remove this thing and let it point to this. And tail O becomes tail O next. So tail O will now come here. Happy or not?
Yes.
Okay. So
Yes,
next one, this link will be broken to point to this. This will stay here. Okay. Then what is tail O? No. Tail O will still point to this. 8 will point to 12. 12 will point to 20. Okay. This link will be there. Okay. Now I have what is HE. Let's see. 2, 4, 6, 8, 12, 20. And what is the odd list? 7, 9. It's still pointing to 12. Okay. So one of them is pointing to null, other one is pointing to this. So if the odd list is opened at all, I will end it. TO next equal to null. So after this, this becomes null. It no longer points to 12. And if the even header is already open, then this is null. One of this is not necessary. But anyway, there is no point. There is no harm in doing both. Then you say star LO equal to HO, star L equal to HE as here.
Sir. Sir, here both the lists are opened, but if we assign like the T next to null, it would be a problem, right? Because the list would end at 8.
No, what is this one?
Yes,
if
sir.
The header is open.
Yes.
Tail is also pointing somewhere.
Yes.
Okay.
But
Yeah,
here we cannot assign TO next as null, right? Because here TO is like
9.
9. Yeah, but
it is currently pointing to 12.
Yes. Yes.
But I have not adjusted this pointer because I have not found any other odd element in the list. The tail,
Seven.
right? 7, 9. I didn't find any other odd element. If I found one, then I would have bypassed that 9, this tail, that link or that next to that element. But here I have not found. So I have to forcibly terminate this list and this list. In this case, this list termination is automatic, but this I have not yet terminated. Yes or no?
Sir, but in the even case, in the next if statement, if you just open the code.
Which one?
Sir,
This one.
yeah. So it says if HE means if HE is open, then TE next equal to null.
It was already null, but if I additionally set it null, it's not a problem, right?
So where, like at this point, where does TE point? 20, right?
It will eventually it will point to this.
Okay. That was my confusion. It was in the diagram.
Okay. I didn't update this T. H will eventually also come here, and it's eventually H becomes null.
Yeah, got it.
Okay. It's a lousy drawing. It would be nice if I could have some animation, but I do not have an animation for this. Okay. So that is about splitting. And
But why are we using in this case node star star LO instead of node star LO?
this is because in C, everything is called by value. Yes or no?
Yes, sir.
Okay. So if I simply said node star LO, then that address will be copied. Whatever change you make to that address inside this function will not be visible outside. But if you make any change to star LO, that will be visible. But I want to change this LO itself. Happy or not?
Yes.
Okay, that's the reason I have to do this. Okay, so I would prefer to do one more thing. So after I have done this, and is it now clear? L is pointing here, HE is also pointing here, but I have readjusted this link. So L will essentially point to the same list as HE is doing.
Sir, so if the first element is even, then the odd list gets delinked from the original one, and
exactly. And converse.
Vice versa.
Yeah, exactly. Okay, so I will quickly write another code, although I am running out of time. I have already run out of time. So let's say I just write the code, run it, and leave the explanation to your imagination. Join. Say header 1. I will just undo this process. I will join this odd list and even list into a single sorted list. Okay. So okay, so this is another way of writing. If H1 is equal to null and H2 is equal to null, so that both the input lists are empty, so I will simply return null. If H1 is null, then return H2. First list is empty, so the joined list will be simply the second list. Likewise, if the second list is null, return H1. Otherwise, I have a situation where both the lists are non-null. Okay. Okay. So as long as H1 is not null or H2 is not null. Maybe I do this. H1 data, if this is less than equal to H2 data, well, I need two assignments. Maybe let me do initialize H. Not only a head node, I need a tail node. Else, so I am starting the joined list. H2, whichever is smaller, I am starting the merged list at that point. H1 is smaller than this, otherwise. If H1 has ended, break. If H2 has ended, let T next point to the remaining part of this H1, break. Otherwise, H1 data is smaller or maybe equal to I will consume from list 1, otherwise I will consume from list 2, and here I will return H. Happy or not? Okay, so let us see. Now what I am doing, merging. So what I will do, L equal to, what name did I give? Join. Maybe just like this. Okay, if there is no bug, let us see what happens. 277, 79, 85, 85. There is some problem, right? There is some problem. Let us debug. If not H1, that is if H1 is null, T next equal to H2, break. T next equal to H1.
Next,
I understand.
in if analysis,
I didn't.
H2 equal to H2 dot.
T equal to T next. Now I have to do this. Otherwise, how will it work? Tail should proceed, right? Something is added to this tail. Okay, tail should be tail next. Okay, that was the omission. So 1, 5, 19, 24, 24, 25, 26, 31, 33. Okay, the original thing is returned. 19. 22, 23, 42, 43, 43, 56, 66, 88, 89. Okay, so you figure out how this is working. This is a sorted merge or sorted join. I just briefly explain. The initial things are fine. If H1 is null and H2 is null, then definitely both the input lists are null. I am returning null. Otherwise, if only the first list is null, then I am returning the second list. If the second list is null, I am returning the first list. Okay. Actually, this condition is not needed. Okay, it is checked here. If H2 is null, that will be returned anyway. That's fine. The first condition is not needed. Otherwise, both H1 is non-null, H2 is non-null, so both lists are non-empty. So I am opening the merged list at the smaller, what is that called? At the smaller node. Whichever data is smaller, I am opening it there. And then, as long as the lists are not exhausted, at least one list is not exhausted. So here it says that H1 is exhausted. So whatever else is staying there, they must be simply appended from H2. So I will simply say T next equal to H2 and base break. Otherwise, if H2 is exhausted first, then T next equal to H1 and break. Otherwise, both lists are not exhausted. So I will once again compare. Whichever is smaller, I will set to that node and H1 equal to H1 next, or H2 equal to H1 next, and here T equal to T next. Return next. Okay. So you look at this. I will once again upload this file. And you convince yourself that this merge routine also works. Anyway, I think I have overshoot the time.
Excuse me.
Yeah, tell.
So I have doubt regarding reversing the list. So actually, I am not able to understand how to reverse the list using that
Reverse the list
itself.
You reverse the links or reverse printing.
Means, yes, sir. Yes.
Which one?
So printing is done, sir. But how? So any linked list, how to?
Okay, so
We
you
need to have linked list in main function.
If I have a list like this, I want to have a list like this, 7, 6, 3, 5, just the opposite thing. Is this the thing you are talking about? It's not printing, but just reversing the links.
Yes, sir.
Yeah, this is the problem you are talking about, right? Yeah, so
Yes, sir.
what should you do? You eventually have to, this becomes this becomes this becomes this, and eventually you have a pointer that you will return, and this pointer will be null. Okay, so I request you to complete this code. And in fact, this is given in many places. 7635. This is not a difficult thing, but for a beginner, it's a good exercise. Okay, like merge and split, this is another good exercise. So I leave it to you as an exercise. Okay. If I had time, I
Thank you, sir.
Okay. Yeah, it's a good exercise. Do it.
Okay, sir.
Okay. Okay, so let us stop today here, and next week maybe we will look at some other remaining topics, like Searching we have covered. Sorting maybe a little bit on sorting. And if time permits, I will talk a little bit about stacks and queues. Okay, so I think we stop here. It's already a long session for today.
So what will be the syllabus of tomorrow's PDS assignment in lab?
Ask your teacher. I will let them know how much is covered. I will let them know.
Sir, also on the PDS website, the slides haven't been uploaded of linked list.
Up to what point? Okay, I will update. Up to whatever point it is given, after that I will update. Okay. Okay, I will do. I will do. Okay. Okay, so shall we stop?
Okay, sir.
Okay, then I will stop recording.
Thank you, sir.
Thank you, sir.
Thank